I refer to today's lesson as properties of the cross product. So similar to what we did with the dot product and also with vector addition, we start to ask ourselves these kind of questions. Remember, this is called the commutative property. So think about each of these as we go through it. Does this hold? Is A cross with B going to be the same as B cross with A? That was true for vector addition. It was true for the dot product. Is it true for the cross product? If you think about it for just a minute, I think you'll be able to come up with the answer. Okay, it is not true. Why do I know that it is not true? Well, imagine the two vectors A and B. You can think about it geometrically if you want. So there's my two vectors A and B. And let's say that this one's vector A, and I'll make this one vector B. Okay. Well, if we remember geometrically the right-hand rule, A crossed with B, if I'm looking at this as the flat surface, would go into the screen or into the page. Whereas B crossed with A, if I curl my right hand, remember my thumb points in the direction of the cross product, B crossed with A would come out of the page. So clearly they're not the same vector. One goes into the page and one goes out of the page. However, they would have the same magnitude. So they'd have the same magnitude because, of course, the magnitude of the cross product is just the magnitude of each vector times the sine of the angle between them. That doesn't matter which one is A and which one is B. So actually, we can add a little negative sign. And if we add that negative sign, now that becomes true. It's called the anti-commutative property. Sorry, my writing's a little messy. It's the same as subtraction, actually. Subtraction has the anti-commutative property as well, because when you subtract 7 minus 4, you get 3, but 4 minus 7 is negative 3, so it's very similar to that. The next property is the distributive property, and it does actually hold. The cross product, similar to the dot product, is distributive over vector addition. We can show that the same way that we showed the dot product is distributive, basically by setting up a proof, with 3 vectors and their components and showing the left side and the right side give you the same thing. It's a nasty proof, but it can be done. Next, we have the little property of scalar multiplication. This shouldn't be surprising either. If you want to take a cross product and apply scalar multiplication to it, you could instead just apply the scalar multiplication to either the first or the second vector. And the reason that's true is that this k value doesn't change the direction of A cross B. It doesn't change the direction of A. It doesn't change the direction of B unless it happens to be negative, in which case it switches the direction, and that's fine. So, and then again, you can see the magnitude equation here. If the magnitude of a cross product is the magnitude of A times the magnitude of B times the sine of theta, then if you want to throw a k in front of that, it doesn't matter, if you just increase one of these instead. So I think that should make a lot of sense. I'm not sure if I explained it all that well. A cross with A. What happens when you cross a vector with itself? Well, let's think about what we would get. Again, we can use this idea. We know the magnitude of the cross product is the magnitude of A times the magnitude of B times the sine of the angle between them. So this would then be the magnitude of A times the magnitude of A times the sine of the angle between them, which is 0. The sine of 0 is 0, and so when you cross a vector with itself, you will get the 0 vector. So as soon as the magnitude of the vector is 0, you don't need to worry about its direction. It doesn't have any direction. It's the 0 vector. In fact, we can go quite a bit further than that, and we can say that two vectors A and B are collinear if and only if their cross product gives you the 0 vector. So forget about multiplying or crossing a vector with itself. How about just crossing any two vectors that are collinear? Remember, we talked about the fact that two vectors that are collinear are parallel. One is drawn on top of the other. It seems like it'd be easy to find a vector perpendicular to both. Could go up, could go down. Actually, it could come out of the page, into the page. In fact, there's an infinite number of vectors that are perpendicular to both of these vectors. In any case, let's get back to this. So we're gonna just quickly prove it. So imagine that we'll start with the if part. If A cross with B is equal to 0, then we want to show the vectors must be collinear. Well, if A cross with B is equal to 0, it must be that the magnitude of A times the magnitude of B times the sine of the angle between them is equal to 0. Well, if A and B, I guess we should say that A and B are not zero vectors themselves. I maybe should add that to the question, but in any case, we'll assume that they're non-zero vectors. And if they're non-zero vectors, that means that sine theta must be 0, which means that theta is 0 degrees or 180 degrees, in which case we know that the vectors must be collinear because they either have the same direction or the opposite direction. So we can say, therefore, the vectors are in fact collinear. On the other side of the proof, we would start with the fact that A and B are collinear and show that they're, so we're assuming that they are collinear. Then we need to show that their cross product will be equal to the 0 vector. It's the other half of the if and only if proof. So if A and B are collinear, that means that theta is equal, it's just the backwards of that proof, is 0 degrees or 180 degrees. And therefore the magnitude of A crossed with B is the magnitude of A times the magnitude of B times the sine of theta. Well, if this is true, then sine theta must be equal to 0, and we get that the A crossed with B has to be equal to 0. So just a mini little proof there, okay? 1/2, if A crossed with B is equal to 0, then AB sine theta equals 0, and sine theta must be 0, so the vectors are collinear since their angle is 0 or 180. I should probably add a sentence like that. If I had some room, I'd do that. And then the other side of the proof is if A and B are collinear, then the angle between them is 0 and 180, and in either case, the sine of both those angles is 0, and hence the cross product gives you the 0 vector. And there you have it. One of the important parts of this lesson is introducing what's called the triple scalar product. So the triple scalar product between vectors A, B, and C is defined as A crossed with B dotted with C. And notice the brackets here imply that you must cross before you dot. However, I'd like to point out that even without the brackets, you know that you must do the cross product first. And the reason is very simple. If you dotted first, so imagine for some strange reason, you decided to do this first, B dotted with C, well then you have a scalar, and you cannot cross a scalar with a vector. So this is the only way it makes sense is to do A cross with B first. So sometimes you'll see the triple scalar product written without the brackets. They're not needed because you know what order you have to do it in. I prefer to write the brackets. Why make life more confusing? Okay, so let's just talk about what this means. A cross with B dotted with C. What if that equals 0? What if it doesn't equal 0? It actually tells you something about the vectors. I always ask this in class, and I usually will get somebody who gets an answer. Let me just try to draw it out for you, and we'll see what we get here. So A crossed with B dotted with C. I've got it up here again. So let's add some vectors here. So let's say that this is vector A right here. Okay, and I'm going to draw vector B right here. Notice that these are both on the screen, even though they're three-dimensional vectors. I've drawn them both on the screen. I mean, I have to. I don't have any other choice about where to put things. But I just want to point something out, that any two vectors can be drawn on the same flat surface. So imagine vector B wasn't on the screen. Imagine it like came out of the screen. Well, that's fine. I could just tilt my entire screen, and now the screen that there's still one plane or one flat surface that these two vectors are drawn on. Any two vectors can be drawn on a flat surface. You just move your flat surface. Okay. How about A crossed with B? So A crossed with B is now some new vector that's perpendicular to both A and B. And let me move these a bit so we can kind of see that. If you draw the vectors kind of like this, okay, and then I draw A crossed with B, you can kind of visualize A crossed with B being perpendicular to both B and both A. So there's A crossed with B. In class, I would literally take a ruler, I would draw A and B on the blackboard, and I take up my meter stick, and I have it coming out of the board, and I say that's now A crossed with B. Okay, so there's a third vector, C. So let's start with the idea that when you take A crossed with B, which is the vector here, and you dot it with C, you get 0. What does that mean if you dot a vector with another vector and get 0? It means they're perpendicular. So if A cross with B, which is this vector here, is dotted with a third vector and you get 0, it must be that vector C, it must be that these two vectors are perpendicular. When I say these two vectors, I mean this entire vector right here and vector C are perpendicular. So where is C going to be if it's perpendicular to AB? It's got to be on the same plane as these two vectors here. It could be, maybe vector C is in here. Okay, or it could be down here, but it's still in this sort of flat, you can imagine this flat surface I'm creating. Basically in class, so what that means is that A, B, and C can be drawn in the same plane, or it can be drawn in the same flat surface. If A crossed with B is perpendicular to C, then C must exist on this same flat surface. I'll try to explain what I do in class. In class, I would draw three vectors on the board, or two vectors on the board, pardon me. I take my ruler and I make it A cross with B, and then I say, where's vector C got to be? And you realize vector C also has to be on the blackboard as well. So these three vectors can be drawn in the same plane, and the conclusion that we make here is that that's called coplanar. Can be drawn in the same plane is coplanar. Kind of like collinear, but can be drawn in the same plane. Any two vectors, by the way, are coplanar. Any two. Okay, 3 may or may not be. Then, of course, if we don't get 0, okay, I could think about drawing this picture again with A and with B. Okay, those define kind of a plane, a flat surface that you kind of have to imagine. A crossed with B is perpendicular to both of them, like this. And then if this time, if I do the triple scalar product and I don't get 0, well, it must be that vector A crossed with B, it must be that it is not perpendicular to C. So vector C is somewhere else, but it is not on the same plane as A and B because it's not perpendicular. So maybe it's really hard to think about it on a 3D surface, but it can't be on this same plane. It's not perpendicular to A. And so in that case, we'd say the vectors are what's called non-coplanar. I can't stress how important vectors being coplanar and non-coplanar is. It is a really, really important idea. You get to the point in, the vector stuff we're working on is the beginning of linear algebra. In linear algebra, they say the vectors are if they're non-coplanar, they're linearly independent. They're definitely different vectors. We get into a little bit of that in this course, and it becomes very important when we talk about planes and lines and 3-space and stuff. But really important idea. So make sure you understood that little part of the lesson. Okay, here I talked about the area of a parallelogram. So lots of times in this course, we've seen that any two vectors kind of form a parallelogram when they're tail to tail. So let's just imagine our two vectors here, and we've completed the parallelogram. And I'll call this vector A down here, and vector B right here, and of course the angle between them is right there. One thing we've learned is that if you do A plus B, that's the length of the diagonal, and A minus B would be the length of this diagonal right here. We're going to learn something else, though. Let's talk about the area of this parallelogram. So the area of a parallelogram is equal to the base times the height. Okay? Now, the base is clearly, in this example, the magnitude of A. That's the base of the parallelogram. And then the height can be seen right here. Don't worry about the arrow there. Just ignore that. Okay? I'll call that H. And I can actually calculate the height because look, the sine of theta is equal to the height opposite over adjacent, which is the magnitude of B. So really, the height of the parallelogram is the magnitude of B times the sine of theta. Just using some simple trigonometry. And so I can replace that for H right here. And I get the magnitude of B times the sine of theta. Now, hopefully something interesting pops out to you here, because notice that this is the magnitude of the cross product. And I think that's kind of interesting. Back to our parallelogram. You set up vectors A and B with the angle between them. The length of the diagonal gives you the sum. The other diagonal gives you the difference. And the magnitude of the cross product actually gives you the area of the parallelogram. Well, if you have a triangle with two vectors, it's obviously going to be very similar. Okay, oh, let me just fix that. Okay, if you've got A and B, like so, well, any parallelogram, or sorry, any triangle is really just half of a parallelogram. I mean, that's where the formula base times height divided by 2 comes in. So the area of a triangle would just obviously be the magnitude of their cross product divided by 2. Okay, and I point that out because we're going to do an example with that. Okay, let's take a look at this next example. And the first thing that I think you should notice is that this example actually has nothing to do with vectors in the question. It's just 3 points in space, and you could draw lines to connect all 3 points and create a triangle, and we want to find the area of that triangle. So although it doesn't involve vectors, we're going to use vectors to solve it. Three-dimensional coordinate geometry is difficult to work with if you don't have vectors to work with, which is why we introduce vectors before we talk about points in the XYZ coordinate system. So any 3 points, as long as the points aren't collinear, any 3 points in space will form a triangle. Let me show you what that would look like in our 3D plotter. So you can say here, I've put these 3 points in, there they are, you can take a look at them, you can imagine connecting them, and they would in fact form a triangle, and it doesn't even matter where these points are exactly. Like I said, as long as they don't fall in a straight line, they do form a triangle. Now, we don't really need that picture to do this question. I mean, we just imagine some triangle between A, B, and C. Now, it doesn't really matter how I label the triangle. I will go A, B, and C. And then I can use this formula on the other page, sorry, back up here, to calculate the area of the triangle. But notice I need vectors, and I don't have vectors here. I have points. These are not vectors. So what I need to do is I need to define some point-to-point vectors. I could do these two, A and B and A and C. That's one way to do it. There is more than one way you could do this. You could do AB and AC. Okay, you could do AB, you could do, BC and BA, that would work, or CB and CA, that would work, but you need 2 vectors, point-to-point vectors, whose tail is at the same location in order to use the definition we just did. So remember, when you're doing point-to-point vectors, you subtract. So AB is -3 minus 1, which is -4, and 2 minus 2 is 0, and 1 minus 3 is -2. So there's the vector that represents AB. The vector that goes from A to C, 2 minus 1 is 1. 3 minus 2 is 1, and -1 minus 3 is -4. So those are the 2 vectors that I'm going to use here. And I need now know that the area of this triangle is the magnitude of the cross product of AB crossed with AC divided by 2. So the next step is actually to figure out, well, what is AB crossed with AC? Hopefully you're pretty good at doing that now. So to do this cross product, of course, I'm going to write AB out twice. And then AC down below twice as well. Take that out and that out. Okay, and then look, here's 0 subtract -2 is in fact +2. Okay, for the next one, I get -2 subtract, that's +16. -2 subtract 16 is -18. And for the last one, I get -4 subtract 0, which is -4. So I get 2, -18, -4. I believe that that is correct. If you check by, dotting that with AB and AC, you should get 0 in both cases. Okay, I'm just doing that in my head right now, and it looks like I am good. Okay, -8 plus 8, yep. So then my area, back down to here, is the magnitude of that vector, 2, -18, -4, and then divided by 2. Now, the magnitude of the cross product, I know you instantly think about AB times AC times the sine of the angle between them. That's great when you have the angle. When you don't have the angle, well, we're just looking for the magnitude of this vector. So this is not a problem. Okay, we can just use the formula for calculating the magnitude of a vector. it's going to be equal to the square root, sorry, this is area, not AB. And why don't we make this note a little neater and we'll just get rid of that. So the area, not AB, is equal to, so I'm going to square each of those like so, and then your area, if you figure that out, you should get the square root of 344 over 2, so something like that. Oops. Okay, not really important what that number is, but there it is, the area. Square root of 344 divided by 2 units squared, whatever the units are on that. Okay, here we are back to the parallelopiped again. And let's take a look at this. Now, the volume of this three-dimensional figure is not surprisingly the area of the base times the height. Since it's a congruent parallelogram over and over and over again for the height, hopefully that volume formula makes sense. Now, let's talk about this with vectors. We're going to talk about vectors A, B, and C. So I'm going to say that vector A is this vector right here. And vector B we'll say is this vector right here. And that makes this vector here vector C. So I'm going to call them A, B, and C just in the order I drew them. So there's this A, B, and C. Okay, and they're all located there. So as soon as you draw three vectors, assuming the vectors are non-coplanar, then you can fill in a three-dimensional parallelogram or that parallelopiped, hard to say. So let's take a look at how we can figure out the volume of this shape, and we can actually use these three vectors. Well, the area of the base we've already realized is this right here, is the vectors made by B and C. So that's just the magnitude of the cross product of B and C. Okay, now we need to think about the height. Now the height can be seen if I draw it. I'm going to draw the height right here. Best I can, okay? Let me just try that again. Okay, there it is there. Okay, the red line represents the height of the parallelepiped. So, how do we figure out the height? Well, I would like you to notice something. Think about B crossed with C. If I draw B crossed with C, notice that that is also a vector that has the same kind of direction as the height. It's possible that it has opposite direction, but I could draw it like that. Okay, there, just change the color and label it. So there's B crossed with C, either that direction or that direction. We don't know how long it is, but that doesn't matter. But what I do notice is that if I were to, and sometimes students will get this in class, how can I calculate the height based on this information? If you look closely, and it's going to be a little bit hard to draw, but if you project A onto B crossed with C, you actually get the height. So the height is actually equal to vector A projected onto B crossed with C. And even if B crossed with C happens to go in the opposite direction, that doesn't matter, because based on our definition of projections, it's still the projection of A onto BC is still going to be the vector that represents the height. So what we can say is we can say that the height is really just the magnitude of the projection of A onto B crossed with C. Okay, and based on our formula for that, for the magnitude of a projection, it's just the absolute value of A dotted with B crossed with C, all divided by the magnitude of B crossed with C. Okay, so I'm just using the definition of, our definitions or formulas for projections from the other day. Okay, this is an absolute value because this is A dotted with B cross with C. It's a scalar, so the absolute value of the scalar divided by the magnitude of B cross with C. So I'm just getting that from, we did the projection of A onto B. Okay, well this is A onto B cross with C. So instead of A dot B divided by the magnitude of B, it's A dot B cross with C divided by the magnitude of B cross with C. Okay, I know that's a little bit tough to see there to understand that, but B cross with C goes this way, and if I were to project vector A onto that B cross with C, I would in fact get the vector that represents the height, and I only care about the value of the height of this parallelepiped, I don't care about the vector, so I'm just using its magnitude. So if I then go ahead and throw the height into this equation here, I will get B crossed with C times whatever I had here, which is A dotted with B crossed with C, just like that. Clean that up a bit, okay, divided by the magnitude of B crossed with C. So just replacing that height with the projection, and then look what happens. Notice the B crossed with C's will divide out, and for our answer, you are just going to get A dotted with B crossed with C. And look at that, there's the triple scalar product. So this is an absolute value symbol, okay, because B crossed with C is a vector, dotted gives you a scalar, so the absolute value of that scalar. So kind of interesting, if you got three vectors, the absolute value of the triple scalar product will actually give you the volume of that three-dimensional parallelepiped that the three vectors make up. Okay, and there's some questions for you guys to work on. Now for page 186, number 8, it's asking you to do a proof, and it's asking you to prove using components. Now, when they say components, so number 8, so for 8a, for example, you're asked to show that U crossed with V is equal to negative V crossed with U. And when they say use components, they mean basically starting off by saying let U equal, U1, U2, U3, and let V equal V1, V2, V3. Now, if you're like me, I hate using U's and V's in my proofs because they look a lot alike. I prefer A and B or X and Y. And they're asking you to show the left side and the right side are the same. Okay, so it's not that bad to do. I've said the geometric proof is shorter, just as in the idea that, look, one is going into the page and one is going out of the page, and just kind of using the right-hand rule to discuss why that's true is actually an okay proof. But they've asked you to use components, and it's not a bad idea. Okay, so I'll let you try those, and just let me know if you have any trouble.